Today's notes, we learn a shortcut on ways to prove that triangles are congruent given enough information. I will warn you right now, the shortcuts take a little bit of work to understand, so you may need to watch the video a second time to totally understand these. So before we do that, we need to talk about two definitions. The first is perpendicular bisector. And the perpendicular bisector of a segment is a segment that is not only perpendicular to it, but it also bisects it. So if you want to think of this in terms of triangles, it's an altitude and it's a median at the same time. Equidistant has to do with the distance that a point is from two others. So 2 points are said to be equidistant from a third if they are the same distance from that third point. So in this diagram here, we know that B, this point right there, is equidistant from A and C because B is the same distance. We know that because we're marking off that AB and BC are congruent. So that means that the distance from B to A is the same as the distance from B to C. So effectively what we have here is two sides being congruent gives us one equidistant point. Our shortcuts are this. The equidistance theorem says if 2 points are equidistant from the endpoints of a segment, then they form the perpendicular bisector of the segment. The way we're going to write this in the proof is equidistance implies perpendicular bisector. So thinking about that last example we just did, we had two segments congruent, gave us one equidistant point. If we need 2 points equidistant, we're going to need two pairs of congruent segments to establish those equidistant points. The reverse is the second theorem. It says if a point is on the perpendicular bisector, then it's equidistant from the endpoints of the segment. So any point that is on that perpendicular bisector is going to have a segment going to the endpoints that are congruent. So how does this work in a proof? Well, let's mark off everything we know. AB is congruent to BK. And we also know that C is the midpoint of AK. So I'm going to go ahead and mark that up. And I'm going to start my proof. So I'm going to say that AC is congruent to CK. Or if you want, KC. And I know that because a midpoint creates two congruent segments. And before the shortcut, in order to do this, we would have to show that BC was congruent to itself by reflexive property. We would have to show that the triangles are congruent. Triangle BCA and triangle BCK are congruent by side, side, side. Then I would have to show that angle BCA was congruent to angle BCK by CPCTC. Then I would have to show that angle BCA and BCK are right angles. And then I would have to show that BC is perpendicular to AK. Well, that's great. But there's an easier way. So if we look at the points B and C, those are really interesting points to me. If I look at B, B is the same distance from A as it is from K. And I know that because these segments are congruent. So B is considered equidistant from A and K. The same thing can be said about C. That C is the same distance from A as it is from K, because those segments are congruent. So what I have are 2 points, B and C, that are both equidistant points to A and K. What they form then is the perpendicular bisector. And let's just state that again. The 2 points that are equidistant from the endpoints of that segment form the perpendicular bisector of that segment. So my statement here for the next step, I'm actually exactly where I need to be. BC is perpendicular to AK. And I know that because I'm going to use the equidistance theorem that says equidistance implies perpendicular bisector. Now, if you're only using the perpendicular aspect, the bisector aspect, whatever, you're still going to use that same reason. Equidistance gives you a perpendicular bisector, even though we're only using the fact that it's perpendicular. Example number 2 looks like it's backwards, and look where with the given information. They're telling us you have a perpendicular bisector. That should be a giveaway once we're done with all of this, that we're going to use that second one. Perpendicular bisector gives you equidistant. So PI is the perpendicular bisector. Let me highlight that entire line. It's not necessarily just the segment. Any point that's on PI is equidistant from R to N. So that means if I needed it, PR and PN are congruent. IR and IN are congruent. TR and TN are congruent. Any point I can pick on there has to be the same distance from R as it is from N. Now let's think about what we're trying to prove. We're trying to show that these angles are congruent. You know what? I really just need to ignore all this stuff down here. It doesn't matter to me. Because what I need to know is that PN and PR are congruent. And we already talked about the reason why that's true. That point P is on the perpendicular bisector, so that means that it's going to be the same distance from the endpoints, R and N. So statement 2, I'm going to say that RP is congruent to PN. And now, because I started with the perpendicular bisector, I start with the perpendicular bisector, which gives me equidistance. And again, that equidistant point was P. It's the same distance to R as it is to N. And now that I know that I have two sides congruent, I have to have two angles congruent. PRI is congruent to angle PNI. If sides then angles. So any point that's on the perpendicular bisector will be the same distance from R as it is from N. I happen to pick P because that would eventually get me my angles, so I knew that PR was congruent to PN.